and I'll expand the screen. And let's see, maybe that's not a bad place to have the my thing. So I'm going to try to make this work. Oh, actually, I found out it works better like this. You can't see what I'm doing, but I'm moving my image of myself, which is not very good, down to the bottom. I found out this the last couple of classes. Finally, someone told me, I didn't realize it. I think I mentioned to you before, this is a new computer for me. It's one provided from the school finally after a long time of being without a computer here. They finally provided this one, and evidently its microphone is very directional, I'll put it that way, because they said when I turned my head like that, they couldn't hear me talk. Did you find that to be the case?
A little bit the first day.
Okay. Well, I've had students in the last two classes I've taught complain about it, so I've started trying to talk directly into the computer. So rather than having my book over on the side, I'm going to have it right in front. I'll be sitting on top of my computer. And then when I show things, that's why I moved my picture down here. Okay, when I show things, the camera is up here so I can see what I'm looking at down here. And I'm still talking to the computer. So I'm trying those kind of devices to try to make it better. Now, I just had this is a general question. Did you happen to go and look at a YouTube video show? What I'm wondering is when I hold up something to the camera for the camera to see, does that show up on the YouTube video? See, I know.
I haven't looked at it yet.
Yeah, no one else has either, so I don't know why I'm doing the YouTube. It's for the people who aren't here, and you've been here, so.
Yeah, I've been writing down everything you say. So
yeah, I knew you had. I could see you doing it. All right, so we will pick up and go from where we left off, and I'll try it with the facing the microphone all the time and trying to get a better shot in the camera. Okay, now what happens sometimes is my image goes away, and especially if there's multiple people in the class, their blocks will show up there and their name. And then I can't see what the camera's showing. Right now I can see what the camera's showing, and I'll try to get paper in front of my face as soon as possible, so you won't have to look at me anymore. Okay. My memory is we're in chapter 1, Systems of Linear Equations, section 1.2, which is Gauss elimination and Gauss-Jordan elimination. And we are on page 19. Now, do you have an actual book or e-book, or are you just doing everything that write down?
I have the e-book, but it's the same as yours.
Right, okay. Does it have page numbers? That's what I don't know.
Yes, sir. I can type in page numbers.
Oh, okay. I didn't know. Okay. Because some people, in some text, I guess it doesn't show up, and they said it's no good for me to tell them page numbers. But usually I say that just in case someone has a book. All right. So anyway, we mentioned Gauss-Jordan elimination before. This is when you do reduced row echelon form. Okay. Row echelon form is just having zeros below the leading ones. Reduced row echelon forms is zeros above and below the leading ones, okay? And this is called Gauss-Jordan elimination. Carl Friedrich Gauss, same one as Gauss elimination, now with Wilhelm Jordan, who was, I think, a German mathematician who came along a century or two later and improved on Gauss's elimination. So example 7 is where I have that we're beginning. Is that where you were?
Yes, sir.
Okay. And this, by the way, is also available at larsonlinearalgebra.com for an interactive version of this type of an example. So if there are, I think someone else added to the class. Okay. I don't know. Do you know Emmanuel Pullum?
Yes, sir. I've had class with him before.
Okay. I think he may have added this class. And that's why I was sort of killing time. I was hoping he was going to show up. And Ricky was here last time, but so far she's not here today either. So maybe that's what it was, that someone else added in your class rather than that you were in another class. I don't remember what had me thinking wrong. But anyway, if you happen not to have a book, you can go to LarsonLinearAlgebra.com and see this example worked out or something very similar to it. So here's what we've got. And since you got a book, I'm not going to write all this down, okay? It seems like Ricky didn't have a book, so I was writing stuff down. But here's the example we're doing. Here is a system of equations, right?
All right.
Okay. Let me get closer and see if this thing right here is bugging me. Okay. There's a system of equations. 3 equations, 3 unknowns. Okay. Believe I've seen that system before. Okay. Now, I think this is example 3, either in the earlier section or this section. There's a system of equations. What's the first thing we do? We write down the augmented matrix from the coefficients and the constants. Now, am I coming across okay in volume? Or am I fading out?
It's fading out a little bit when the book goes.
Okay, I think the book's in the way, so I'll try to talk under the book. Okay, this is not easy. I don't think I can get under the book because it's at the top of the page. So I'll try to talk around the book. Okay, let me get it back on here. There's the equation.
Yeah, I can see it, but it's still fading out. You can barely hear you.
Okay. See, this is such a directional sound system. So you got the book, so I won't show it anymore. Okay? So what we do is write down the augmented matrix that consists of the coefficients of those of that system of equations, and augmented with the constants at the side. Now, where they go in the book, they jump right to where they left off in example 3. Are you okay with doing that, or would it be beneficial to redo those steps?
It doesn't matter to me. I already have it wrote down.
Okay, good. All right, so we'll pick up where they pick up, and this is from that augmented matrix, row reduced, okay, to Gauss form, Gauss elimination. So that was a 1, -2, 3, 9. Okay. One reason I don't like doing it this way, this isn't how I normally do these, but we'll go from this here. Okay. And that, by the way, are the coefficients of that first equation and the constant, augmented form. The second one, though, is when you've added the first 2 equations together, and that gave you a 0. Well, a little beyond that. Yeah, no, that's right. Just add them together. 0, 1, 3, 5. That is the second. Now, the third row is when you multiply the top row by -2 and added it to the third row. That gave you a 0. And then you've also done one more step in there. We won't go into all that. I'll just write it down. 0, 0, 1, 2. Okay. Now, that's where we stopped with Gauss elimination. Okay? I'll try to talk under the paper here. Okay? And we could, because then we could say Z is equal to 2, plug 3 times 2 is 6. Y plus 6 equal 5, so y is -1. Yeah, you could do back substitution here. But what we're going to do now is Gauss-Jordan elimination. We're going to eliminate the numbers above the leading ones, not just those below the leading ones. So the first candidate is that -2 up top. And what would we do to eliminate that -2? To make it a 0? Use the leading one that's below it.
Right.
Right. And what would that be?
Negative multiplied by +2.
Yeah. 2 times row 2 plus row 1 is the new row 1. Okay?
Right.
So, Now, I like to go and write down the row I'm using. I'm using row 2, so write it down. 0, 1, 3, 5. Okay? Now, operate on the top row. Do what we just said to do. 2 times 0, that's in row 2, is 0, plus 1 is 1. See, you don't change that leading 1. You never want to change a leading 1. Yes, then 2 times 1 is 2, minus 2 is 0. That's exactly what we want. You go on from there.
2 times 3 is 6. 6 and 3 is 9.
Perfect.
2 and 5 is 10. 10 and 9 is 19.
Perfect. Okay. Now, as far as that second leading 1 goes, you're happy with the third row. In fact, you're happy with the third row, period. It's 0, 0, 1, 2. So write it down. Okay. Now, the next 2 candidates for change. You got that leading 1 in the third row. Okay, let's start over. You have a leading 1 in the upper left, 0's below it. Perfect. Leading 1 is the first non-zero entry in row 2 is a 1. You got 0 above and below it. Perfect. Then you go to row 3. The first non-zero entry is a 1. You want zeros above that. So you've got 2 operations to do. What's the first one?
To change the second row, you can multiply the third row times, you can multiply the top row times -3.
Okay. No, you multiply the third row by -3. You're right.
Yeah.
And add to the second row, right?
Add to the second row.
Okay. Yeah, you don't multiply the second row by -3 and add to the first, because then you're going to mess up your zeros and ones.
Right.
You don't want to mess up your zeros and ones. So you use the third row. You always use the leading 1. And we're going to do 2 things. I'll go on and say on both. For the top one, we're going to multiply the third row by -9 times row 3 and add it to row 1. That's going to be the new row 1. For the second row, we're going to multiply the bottom row by -3 times row 3 and add that to row 2. And that will be the new row 2. Now, which order you do these, it doesn't matter. You said row 2 first, so let's do row 2 first. First, though, I write down the one I'm not changing. Third row, 0, 0, 1, 2. That came out of Gauss elimination. Perfect. We don't want to change it. Okay, so let's do row 2 then. What would it become?
0.
0.
1.
Perfect.
0.
0.
-1.
-1. Excellent. Okay, and let's go up to row 1. And here you're going to multiply -9 times row 3 and add to row 1. What does that give you?
Keep the 1.
Keep your 1.
0.
Keep the 0.
0.
0.
And 1.
1. Perfect. So what's your solution? X equal 1, Y equal -1, Z equal 2. Boy, Gauss-Jordan makes writing the answers so easy because you don't have to do back substitution. You just write down what they are. Okay. Oh, here's Ricky. Hold on just a moment and let me admit her to the class. Okay. Ricky's here. All right. Now, like I say, I think we added Jemanuel to the class. I'm not sure. I may be thinking of the wrong class. But right now it's perfect attendance unless Jemanuel is now in the class. Ricky, you on board yet?
Yeah.
Okay, good deal. Good to have you. I saw you come in. I didn't know if you had your setup done yet. All right, we started in Chapter 1, Systems of Linear Equations, Section 1.2, Gauss elimination and Gauss-Jordan elimination. We have already done Gauss elimination. We did our first example with Gauss-Jordan elimination, example 7 on page 19. Now, I can't remember. Do you have a book yet or not? E-book or what?
Yeah, I have a book.
Oh, you do have a book. Excellent. Okay, so I'm not going to hold as much stuff up in front of the camera. I will occasionally, but I'll try to make it easier. Now, something I found out.
Also, if it seems like I miss classes is because I had to change locations, so the Wi-Fi here is kind of spotty.
Okay, say that one more time.
I had to change locations, so the Wi-Fi is kind of spotty. So
Uh-huh.
if I miss classes or something like that, it's because the Wi-Fi here is bad.
I see. Okay. Yeah, sometimes ours gets really weak too. And every now and then I'll get a little thing on the screen saying your internet is unstable or something like that. And it's because Wi-Fi is pretty bad. Actually, last term, at the end of last term, when we did go to virtual classes, from what I understood from people who follow this kind of stuff, all of the internet providers started really struggling because they had so much more usage in the day than they were ever used to. Because high schools, grammar schools, colleges, everybody was using their system. And ours, the one that we use is Spectrum. It went downhill. I mean, it crashed, at least in our area, from somewhere in West Georgia through Birmingham. Over in Hueytown, it didn't crash because I had a student from there and he was on Spectrum and he was okay. But from West Georgia to Birmingham, as far as we could tell, the whole system went down for more than 2 days. Just imagine what it was like trying to teach virtual classes with no internet. My wife had a hotspot and it wasn't good, but we did manage to struggle through for more than 2 days until they finally brought it back. And so it was awful. So I know what you're dealing with. I dealt with it last term, and maybe you will want to deal with it again this term as well. But anyway, we've just finished doing example 7 on page 19. And if you got your book, you can read through that. Once I'll upload this to YouTube, then you'll be able to see and hear what we just did on it. But in addition to both of those, you can go right now, or not right now, but right after class to larsonlinearalgebra.com and see an interactive version of this type of an example. Now, I don't remember if I did this before. This time I will be holding up the book. This book has 2 absolutely free, absolutely available sources. One of these is linearalgebra.com. Anyone can go there. You don't need a code. You don't need a class key. You don't even need to own the book. Your grandmother could go in and look at linearalgebra.com. I know she would enjoy doing that, but it has features like this problem we just did. It works it in there. In addition to that, it has calcchat.com, which is all of the odd number exercises in every section are worked out solutions there at calcchat.com. So 2 really, really beneficial sources, absolutely free, no codes, no keys, nothing. You go to them, and now you have to search around and find the problems you're looking for, but they're there, available for your viewing pleasure. Okay. Now, any questions on what we've done so far? Now, at the bottom of page 19 in your text, there is an issue, okay? And it's mentioned here, and they just leave it hanging, okay? But here's what it is. Now, this one I think I will hold up so you can see what I'm talking about, okay? Because this is at the bottom of the page and I can talk under it if I can find it. Nope, there it is. Okay. What if this was your system of equations? Does anything strike you as good, bad, or indifferent about that system of equations? I'll give you a hint. There's no leading one anywhere in the problem. You can't rearrange the variables, you can't rearrange the equations, you can't rearrange anything and come up with a leading one. Okay? To make it even worse than that, in that first equation, none of those, there's no common factor of all those coefficients. In the second equation, there's no common factor of those coefficients. In the third equation, there's no common factor. So the first step you're going to have is to divide, you pick whichever one, they say that first equation divided by 2. Well, then your first row of that system of equations would be a 1, minus 5 halves, 5 halves, I can't read, is that 7? So you have a bunch of fractions. Now, I know y'all love your fractions. Frankly, I don't care for them that much. But it makes the whole mess a lot harder to do. But it's still doable. Fractions are numbers, just like any other numbers. They're just harder to work with. But you can still do it. There's nothing that prevents fractions from being used. Thank goodness they're not going to have us to do it, okay? But you could do that on your spare time if you wanted to. But you flip the page, and it says here, here's another system of equation. Now, you can't hear me. You both got books. I'll let you look at it. It's in the discovery block, okay? It says there, without performing any row operations, explain why the system of linear equations below has to be consistent. Can you think of some reason why it would be consistent? How can we say it guaranteed to be consistent when we haven't done any row reduction at all?
Each equation equals 0? Or?
That's it. This is what we call a homogeneous set of equations, meaning every equation is equal to 0. So to be consistent, that means there's at least one solution. Can you think of one solution for this system of equations? You'll kick yourself as soon as I tell you, unless you see it first. X1 equal 0, X2 equal 0, X3 equals 0. Guaranteed to work, right? Because all three of them are equal to 0, okay? So therefore, it has at least one solution. Now, we call that solution the trivial solution, okay? Anytime you have a homogeneous set of equations, meaning all the equations are equal to 0, you know right off the top that the trivial solution, x1 equals 0, however many equations you got, as long as it's 3 equations, 3 unknowns, you know, well, actually any number, you know that's going to work, okay? Guaranteed. Now, the question might be, is that a unique solution? In other words, could it have more than one? In other words, an infinite number of solutions. It may. We can't tell looking at it, okay? But we do know it has at least one, meaning it's a consistent system. Now look at number 2 there. The system below has more variables than it does equations. Why does that guarantee that you have an infinite number of solutions? Well, think about how we'd go about solving this. If we did Gauss-Jordan elimination, even though this is really ugly and messy and has fractions and everything, you would have the first entry would be a 1 with zeros below it, okay? Now, either the first non-zero entry in the second row would have to be a 1 with zeros above and below it. And if you had any entries in the third row, you may or may not, if you had a leading 1, you would have zeros above it. Well, guess what? You would be left with one arbitrary constant, okay? Something that you could not solve. It may be the third one, it may be the second one, it may be the fourth one. One of those you could not solve, so you would let that equal t, okay? Well, as soon as that's a t, when t is equal to 0, probably everything turns out being a 0 or something. But after that, t could be anything in the world, and every one of those would give you a different coefficient. Okay, I mean a different solution. So that guarantees you have an infinite number of solutions. So anytime you have more equations than you do more unknowns than you do equations, you're going to wind up with infinite number of solutions. If you think about this, x plus y is equal to 1. That's a single equation, two variables, one equation. Well, guess what? 1 plus 0 is 1. 0 plus 1 is 1. 3 minus 2 is 1. You have an infinite number of solutions because you have more variables than you do equations. So that is guaranteed to do. Now, how does a system look when you know you have an infinite number of solutions? That's what example 8 is going to be doing. So let's write it down. Now, I'm not going to write down the system of equations. Both of you have books. You can see it. 2x1 plus 4x2 minus 2x3 is equal to 0, and 3x1 plus 5x2 is equal to 1. I want you to write what and it's in the book, but don't look in the book. You tell me what your augmented matrix is going to look like. What's the augmented matrix? Come on, it's pretty easy. 2, 4, negative 2, 0, 3, 5, 0, 1. Perfect. Now, do you start to panic and sweat a little bit and say, oh no, we don't have a leading 1?
Yeah.
No. Take a look at that first equation. What do you notice about it?
They're all multiples of 2.
Exactly. So we can take that first equation, divide by 2, or multiply by 1/2, however you want to say it, and that gives you an equation that does have a leading 1. What would that first equation be then? 1, 2, negative 1, 0. Perfect. Leave the second equation alone. 3, 5, 0, 1. Okay? Now, what's your mission should you choose to accept it?
You want to make that second equation 0, right?
The 3 to be a 0.
Right.
Right, sure. How do you do that?
Multiply the top equation by negative 3 and add it to
Negative 3 times row 1, add it to row 2, and that gives you a new row 2. So we're using that top equation, leave it alone, 1, 2, negative 1, 0. And what's the new second equation?
0,
0,
negative 1,
negative 1,
positive 3,
3,
and 1.
1. Perfect. Okay. Now, what do you notice about the second equation, and what would you rather it be? It's leading, not...
Would you rather the negative 1 be a 1?
Yes, you want that negative 1 to become a 1. How do we make that happen legally?
I forgot.
Okay, the 3 things you could do. You could either exchange rows. Don't do that. We got that 1 up there where we want it.
Right.
You could add a multiple of 1 row to another row. That's not going to change that minus 1.
Right.
But you could multiply or divide any row by a non-zero. And what would you multiply by or divide by?
Negative 1.
Excellent. Okay. So how I'm going to do that? I'm just going to make that minus a plus, and then the plus a minus, and the plus a minus. So I just made 3 little marks on the page, and I've done that step. Okay. Now we're doing Gauss-Jordan elimination. So what's our next goal?
To make you want to make that 2 a 0?
Excellent. And how will you do that?
Multiply the bottom equation by -2 and add it to the first equation.
Okay, -2 row 2 plus row 1. Perfect, perfect, perfect. Since we're using the bottom row, I'm going to leave it alone. 0, 1, -3, -1. The new top equation becomes
1, 0.
perfect.
+5.
Perfect.
And +2.
+2. Excellent. Okay. Now, guess what? Believe it or not, we've got it in reduced row echelon form. Every row, the first non-zero entry is a 1, and you got zeros below the first one and above the second one. Okay. You can't do anything else. Now, the first column represents your variable x1, right? Your second column represents the variable x2. Okay, we got leading ones there. We're happy. The third column represents your variable x3. We can't do anything with that, so we make that x3 a parameter. And their favorite parameter is usually t, but it doesn't have to be it. You can make it anything. I wouldn't make it x, okay? That would be too confusing. Why not t? So and I actually write it down, let x sub 3 equal t. All right. Now, this is almost like back substitution, but it's not quite the same. Let's write down that first equation. That 1 represents the coefficient for x1. So that would be x1 and 0x2, so you don't have to write anything down there, plus 5 times x3, but x3 is t, so plus 5t is equal to 2. Now, in the old days, back when I was growing up with linear algebra, I used to, with the augmented matrix, I put a little vertical line indicating where those equal signs were, okay? And that way I always remember, oh, that's not a variable, that's a constant over there. This book doesn't do it, so I've gotten away from doing that, but I kind of like that idea. It keeps reminding me. Sometimes I do a dotted line there so you don't confuse it, okay? But that's your constant, so that's why that's equal to a 2, okay? So solve for x1. x1 is equal to 2 minus 5t, right? Okay. And you've already no, you're in Cal 3 now, right?
Yes, sir.
Okay, have y'all started parametric equations, or did you do that in Cal 2?
That's what I'm starting on this week.
Okay, this is a parametric equation right there. See, these two are sort of blending together. So let's do the same thing with x2. That's the second equation. x2 minus 3 times x3, but x3 is t, so minus 3t is equal to minus 1. Remember that last one is an equal sign in between it. So now let's add 3t to both sides. You get x2 is equal to 3t minus 1. It doesn't matter which order you do those. I just don't like leading off with the minus sign, so I put the positive in front. So guess what? Here is our ordered triplet. Your x1 is 2 minus 5t. Your x2 is 3t minus 1. And your x3 is just t. There represents your solution to that problem. Now, you don't have to write it this way, but that's how I chose to, okay? The x's, you could just leave it like we had it there. x1 is equal to 2 minus 5t. I think if I can read my writing backwards, x2 equal 3t minus 1, and x3 is equal to t. Somewhere over there I wrote it down. I can't find it now. Okay. But anyway, that's your solution, where t is any real number. Pick a real number, any real number. T equals 0. Oh, 1. 1 will be fine. That would be -3, 2, 1, right? You get t equal that. If you pick t equals 0, I'm lazier than you are. I picked the easy one. 2, -1, 0, okay? Any t. 4/3 pi. Oh, I don't want to do that one, but that would work. You know, it just gives you an ordered triplet. infinite number of order triplets. So that's what it looks like when you have a system, when you do Gauss-Jordan elimination, and you wind up with a system with infinitely many solutions. And that always will happen if you have more variables than you have equations. Always. Okay. Now, let's move on to, it says, note in example 8 that an arbitrary parameter t represents the non-leading, I'd say non-leading one variable, x3. So that's what you choose. You may have them with more than one, and usually the book will use s and t, or rs and t, or however many it is. They usually use those letters down there. I think in your Cal 3 you'll find they loved using s's and t's too. I don't know why, but they do. Okay. Now, what we did in Discovery on page 20, we're going to do on page 21. Homogeneous. Now, I had one student in one class says, isn't that homogeneous? And I said, well, I guess it could be. So I started calling it both. But then I had a student in a later class, and I was doing both of them, and she said, why do you say it twice? I said, well, I had a student in another class who didn't like homogeneous. He wanted me to say homogeneous. So she pulled out her cell phone, smartphone, and looked it up somewhere that gave pronunciation. She typed it in, and they said the pronunciation is homogeneous. So I'm going back to homogeneous. If you like homogeneous, you can call it that. What it means is everything's equal to 0. All the equations have the constants equal to 0. So your system of equations, remember how we did it? A11x1, A12x2, A13x3, all the way up to A1nxn equals 0. A21x1 plus A22x2 plus A23x3, all the way up to A2nxn equals 0. A31x1, yeah, blah, 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 blah. All the way down to a m1x1 plus a m2x2 plus a m3x3 plus blah, 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 goes up to a mn. If you have m equations, n unknowns, a m x sub n equals 0. They're all equal to 0. Every time you have a situation like that, you know right off the top it's a consistent system because the trivial solution, the obvious solution, all your x's equal 0, have to work. Absolutely guaranteed. But the question is, are there more than that trivial solution? And that's what we're about to do now. So let's solve that homogeneous system. I think I've written everything on here that I can possibly write. Let me go to another piece of paper here. Okay. All right, clean page. Okay, you both got your book, so I'm not going to write down the equation. x1 minus x2 plus 3x3 equals 0. 2x1 plus x2 plus 3x3 equals 0. What's your first step?
You want to make that 2x in the second equation a 0.
Okay, yeah, but, okay. Write down the augmented matrix.
Right, okay.
That's what we do first. Don't carry those x's around if you don't have to. But before we do that, let me back off one. Number one, it's a homogeneous system. That means you know that it has at least one solution, 0, 0, 0. That's guaranteed to work because both equations are 0. Here's another observation. You have more variables than you have equations. So you know absolutely without a shadow of a doubt you're going to have an infinite number of solutions. Okay? So let's see what we've got. So write down the augmented matrix. What will that be?
1, negative 1, 3, and 0.
Got it?
2, 1, 3, and 0.
Perfect. Okay. And what's your first operation you're going to do on that augmented matrix? And that's what you were leading off to tell me.
Multiply the first equation by negative 2 and add it to the second equation.
Negative 2 row 1 plus row 2. Okay. And that will produce Top row is what you're using, so leave it alone. 1 minus 1, 3, 0. Second equation you're fiddling with, so what does that become?
0,
0,
3,
3,
negative 3,
negative 3.
and
I'll do the
0.
last one, 0. Okay, all right. I can do the hard ones, okay. Now, what do you want to happen next?
I would like to make that 3 a 1.
And how do you do that?
I keep forgetting.
It's that third operation you keep forgetting.
Yeah, divide by 3.
Yes, divide by 3. Perfect. What does that give you?
0, 1, negative 1, and 0.
Perfect. And the top row stays the same. 1 minus 1, 3, 0. Right?
All right.
What's the next thing you want to happen?
Try to get that negative 1 in the first equation to 0.
How do you do that? Use that one, the leading one in row 2.
Right.
How can you make that negative 1 in row 1 become a 0 then?
Just add the first
Add
equation.
the first 2 rows together. So row 2 plus row 1 is your new row 1. Okay? So I'm going to leave that second one alone. 0, 1, minus 1, 0. And what's the new first equation?
1,
1,
0,
0,
2,
2,
0.
0. Perfect. Now you're ready to roll. Guess what you got to do? You have a column without a leading 1. So what do you say again?
Let x of 3 equal t.
Okay, perfect. So x of 3 is equal to t. Seems like we've done that before. So let's write that down. X of 3 is equal to t. With that in mind, what does the first equation tell you then?
That, okay, so you got it.
This is when you put your variables back in.
Yeah. X of 1.
X of 1
plus 2t.
T equal
0.
0. Okay?
So x of 1 equals negative 2t.
Perfect. And the second equation tells you
That you got x of 2 minus t equals 0.
Yep, and that tells you?
X of 2 equals negative t.
Nope.
I mean, positive t.
Yeah, equal t. So here's your ordered triplet. You don't have to do this. To me, I find it easy to do. It's negative 2, t, t, t. Uh-oh, you have to go to the bathroom? Never mind, I didn't say that. Okay, all right. All right. Pick a t, any t?
0.
0, 0, 0. We knew that one was work. You didn't need to pick that one. Okay. You're being lazier than me. Okay.
1.
Pick a t equal 1. You get?
Negative 2, 1, 1.
Perfect. Any t you put in there, either 4/3 pi, would be negative 8/3 pi, 4/3 pi, 4/3 pi. Yeah. Any variable, any value you put in for t will give you a solution, not a unique solution, including the trivial solution. Let's see if they got it right in the book. 2t, t, t. Yep, they had to go 2. Okay, got it. Now, this sort of leads to what if you have a homogeneous system with fewer equations than variables? It's guaranteed to have infinitely many solutions. We noted that at the very beginning. So that's what theorem 1.1 tells us. Every homogeneous system of linear equations is consistent. We already determined that because it has at least one solution. Secondly, moreover, if the system has fewer equations than variables, I like to say more variables than equations, it doesn't matter, then it must have infinitely many solutions. Okay? Must have. And guess what? We just finished 1.2. So homework exercises here would be any of the odds. And by the way, I'm going to point this out to you, but I can't really talk around it too much. Look at the top of the page there, and it says see calcchat.com for worked out solutions. I can't read it backwards. For any of the odd number exercises. Okay? So that's where the CalcChat comes into play. So do any of the odds. Okay, now why do I give you odds? Several reasons. Number one, the answers to the odds are in the back of the book. You don't have to go to calcchat.com. When you do your problem, look in the back of the book. If you got the right answer, move on. Okay. Now, if you don't get the right answer, see if you can figure out how you missed it, where you made your error. If you can find that out, super. If you can't, don't panic. Don't waste a lot of time. Don't get burned out. What you can do is go to calcchat.com and see how they got that answer. Okay? Now let me point something else out to you. Notice what follows that statement? A QR code. What does that mean? Don't most of your smartphones read QR codes? You can hold your smartphone right up to that, get it in the viewfinder there. It will take you right to that calcchat.com. So you don't have to go to a computer and do it. You can do it right there on your smartphone. Okay? See what the answer is. See how they got it. Okay. So do any of the odds 1 through 5. They're in the back of the book. They're at calcchat.com. Do either 7 or 9. They're at calcchat.com and in the back of the book. Do any of the odds 11 through 17. Same deal. Do any of the odds 19 to 23. Same deal. Do any of the odds 25 to 37. A whole passel of those. You don't have to do them all. Just do enough so you say, yep, I got this. Move on to the next group. Do any of the odds, either 39 or 41. A bit longer. Okay, either 43 or 45. 47 is applied problem. Okay, 49 is a problem with a variable up there in it, a k. 51's coefficient design. I don't know exactly. Oh, I guess you get to pick them for that last one. Okay, 53. Do that one, CalcChat. 55's a CalcChat. Now 57's a writing problem. You can do that if you want to. I assume it's a CalcChat. You can read and see what they think the answer should be. I'll let you decide what you want to do with 57. 59 is a true-false. So it has 4 parts to it. See if you can figure that out. 61's another writing problem. You can do whatever you want to with that. Okay, 63 is a row equivalent problem, so I'll let you figure that one out. 65, interesting. They introduced a value, a variable, you might say, not really a variable, a value named lambda. Okay? Now, I'm not sure we're going to get there because we have a limited term, but we're going to get as far as we can. But I want you to turn to your table of contents. You don't have to physically do it. You can mentally do it. And if you think about Chapter 7, Chapter 7 is talking about eigenvalues and eigenvectors. Now, so far when teaching this class, I've never gotten that far. We might get there this time. I don't know if we will or not. Those are your lambdas. So this is getting you ready for Chapter 7. So even if we don't get there, you're already making some progress toward that if you can do 65. Okay? 67 is another one that you can certainly do. And 69 is another writing exercise. If you want to do that, you can. All right, enough of that. Let's move on to 1.3. Any questions on 1.2? And by the way, if you remember, the dean, who used to be a elementary school teacher, likes for us to get some type of indication that you're doing the work, okay? So she wants some sort of output every class. She may want it every week. Let's do it every class. So I'd say pick one of those odd number exercises, any one, and turn it in to me. Send it to me in an email. Send it to me as a message on Blackboard. That just lets me know you're keeping up. If you're having trouble with it, indicate that. Say, I don't see how they get this. Where am I going wrong? That would be an excellent, excellent use of these things. If you got it right, send it to me, the correct answer. I'll be happy camper, okay? Now, what will I do with them? I'll just make a little mark. I don't have the grade book set up yet, but I'll make a little mark by every day in class to indicate whether you turned it in or not. And at the end of the term, if you have enough little marks there and you happen to be right on the borderline and 89.2, that's going to be a B. But if you have enough of those little marks by your name, that could get bumped up to an A. Okay? Most of the time, it's not going to make any difference in the own, but only if you're in that borderline case. Now, if you make 89.1, and you don't have any marks by your name, you get the 89.1. You get the B. You earned it. Okay. Now, will it pull up at 81.9? No. It'll make it an 82. No, I mean, it might even make it an 83, but that's still going to be a B. So it's only really going to help in those borderline situations, but it's still, the main place it's going to help, frankly, is when you're doing your test. You're not going to have to go back, oh, how do you do this? How do you do this? You've already done it. You've already sort of mastered it, or at least moved along the way to mastery. So hopefully you can get it done that way. All right. Any questions on that? So please turn into me some sort of thing. Now that means, and here's what she also indicated to us, the faculty. I don't think she ever said it to students this way, but if someone is not here in class, like perhaps Drew Manuel, if he is in the class now, but he couldn't make this class, but he hears that's the assignment, he turns that assignment in, he gets counted as being present. Okay? So that's the other thing it'll do for you. Okay? If you can't be here, if you turn in the assignment, that carts you here. Guess what? What difference does that make anyway? Because once you have at least one attendance, you're going to get your financial aid. So I don't know why they're that bent out of shape about attendance. I don't know. Okay. Anyway, 1.3 applications of systems of linear equations. Now we're not going to do everything in this section. Okay. Some of these things take a lot of time to do, but I'll walk you through them. Here is a picture. You see, you both of you got books. You see that figure there, 1.3. There is a weird-looking polynomial. And I'll just give you a hint. The way it's graphed here, that's obviously an even degree polynomial. It's on the up and up. It has to be an even degree. Okay? Not only that, the leading coefficient has to be positive. That gets it going up. Okay? Now, looking at this, I would say this is at least a fourth degree polynomial. It may be more higher degree than that, but it's at least fourth degree polynomial. So guess what? That's going to require us to know at least 5 points on that to specify what that polynomial is. And there you see them listed. 1, 2, 3, 4, 5. Actually, they list 6. You don't really need 6. Actually, you only need 4. I thought it was 5. It's only 4. Why is that? Because if you think about a polynomial, and they list it here, a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x cubed plus a sub 4x4. That's 5 points. You need at least 5 points. 5 points to define that polynomial. I said it right the first time. They list 6, you don't really need 6. You need at least 5. Because with those 5 points, you can write down 5 polynomial equations. Because guess what? The p of x is the y value. So the first equation would be y1 is equal to a sub 0 plus a1 x1 plus a2 x1 squared plus a3 x1 cubed plus a4 x1 to the 4th. Stop right there. Okay? Second one would be y2 is equal to a0 plus a1 x2 plus a2 x2 squared plus a3 x2 cubed plus a sub 4 x2 to the 4th power. Every one of those you can write down a polynomial equation. And you know what it's equal to? It's equal to the y. Okay? Now, notice what we've got there. Suddenly we turned around from being x being the variable and a being the coefficients, constants. Now you've got 5 equations. You know the x's because you have those 5 x points, right? And you know the y's. So now your a becomes your variable. A0, A1, A2, A3. We don't know what they are. They know they're constants. Here you have a 5 equations with 5 unknowns. The A0, A1, A2, A3, A4. Those are your 5 unknowns. And you can solve that equation. And those are linear equations. Even though your x1s are squared and cubed and raised to the 4th power, those just give you numbers, coefficients of those a's. So that gives you a way to identify what polynomial you're dealing with. Okay? Now example 1. That's obviously a parabola, which is a 2nd degree polynomial, right? So it's going to be your p of x is going to be a0 plus a1x plus a2x squared. There is your generic polynomial equation, okay? And then you plug in these 3 points. You got 3 points, 3 variables, you got it, okay? And you can find out what they are. That sets up a matrix. Solve the matrix, Gauss-Jordan elimination, however you want to solve it. There it is. Okay? Now, do you want to do those just to see how they work? I'm not going to require that on the test. There was nothing in your course description that said you had to do polynomial curve fitting. But if you want to see how this is done, I'll be glad to do that example 1. You want to see it? It's sort of fun to do, but you don't have to if you don't want to. You tell me. Yay or nay?
Nay.
Nay? Okay. Example 2, you can actually go to LarsonLinearAlgebra.com and watch them do it, okay? Here they give you a polynomial, and again, it's going down and down, so it needs to be an even degree polynomial. It has 3 direction changes, so it's got to be at least a 4th degree polynomial. And they give you 1, 2, 3, 4, 5 points on it. That indicates, yep, you should be able to figure out that 4th degree polynomial with those 5 points. And you just plug them in. You write down those points and you plug them in. Now let's say 5 equations with 5 unknowns, your A1, A0, A1, A2, A3, and A4. Those are your 5 unknowns, and it's a pretty hairy looking equation. Now the good news is, look at that one that's 0, 1. You can tell right now what that one is. A0 plus A1 times 0 plus A2 times 0 squared plus A3 times 0 cubed plus A4 times 0 is equal to 1. A1 is equal to 1. Well, now you've just reduced your 5 by 5 equation, a matrix, or a 5 by 6 actually, you could reduce it to a 4 by 5. So that's fairly easy to do. Okay. Now, what's not so easy to do is look at the answers you get with that one. Okay, I didn't look at the answer of the other one. That was pretty big numbers on that one. Example 1, A0 is 24, A1 is negative 28, A2 is 8. Pretty good sized numbers there. Look at example 2. A1 is 1, A0 is 1. We saw that right off the top. A1, negative 5/4, A2, 101 24, A3, 3/4, and A4, negative 17 24. I'm glad you decided not to do that problem. I mean, it's doable, but it's tedious. Awfully tedious. Okay? Now, what if you had something like this one? Example 3. What if you wanted to find the polynomial that fits these 3 points? In 2011, we had 3 cases of this really serious flu. In 2012, we had 5 cases. In 2013, we had 1 case. 2014, we had 4 cases. 2015, it went up to 10 cases. Can you come up with a polynomial that matches that? Frankly, I don't want to raise 2011 or 12 or 13 or 14 or 15 to the 4th power. I just don't want to do that, okay? Well, guess what? You can scale it downward. Let's just say you're going to have, rather than 2011, 2012, 2013, 2014, 2015, let's just say year 1, year 2, year 3, year 4, year 5. And then when we get your answer, put it back in as 2011, 2012, 2013. So that's one way to do it. How they chose to do it, though, they chose the middle term to be your 0 value, 2013. So 2012 would be a -1, 2011 would be a -2, 2014 was a +1, 2015 a +2. Either way you wanted to do it, it would work. Okay? And when you finally get your answer, remember what your x minus something was. Again, it turns into a really hairy look at set of coefficients. That's why I'm really happy not to have to do any of those. Okay. Now, let's look at those are some made up type problems. Let's look at one that is a real live type problem. We're looking at 4 different planets. They are called the terrestrial planets, those that are rocky, Mercury, Venus, Earth, and Mars, and their mean distance from the sun, this is not in miles, but in Earth distances. We call that one astronomical unit, the distance from Earth to sun, so that's 1. So Mercury is 0.387, Venus is 0.723, and Mars is 1.524. And then we'll look at the period of those 3 planets. That's how long it takes it to go 1 revolution around the sun, with, again, Earth year being 1 year. So Mercury goes in 2/10 of a year, Venus goes in 6/10 of a year, and Mars goes in 1.8 years. I'm rounding off, okay? So here you have your table. Let's do a curve fitting there. And since you have 4 variables, they start with a quadratic. Okay, that's not going to use everything. That's only going to use 3 A's, you might say. Okay? So they did it with those 3, and they make Mercury, Venus, and Earth, the curve go right through those. Notice it's off a little bit on Mars, but not bad. Very close for Mars. Okay? Now, that would be part of a parabola. It's not a perfect fit, though. Okay. What does make awfully close to a perfect fit is if you do what they call a log-log transform. Okay? Here, rather than doing the mean distance and the periods in numbers, we do them in the log of those numbers. Okay? Now remember, the log of a fractional number less than 1 but greater than 0 is going to be negative. The log of 1 is 0, so Earth will be 0 in both cases. And the log of a positive number greater than 1 will be a positive number. And so when you do the logs there and then do a curve fitting there, you found out it fits almost perfectly. Well, guess what? There was a guy, I always go blank on his name when I'm trying to say it. Laws of planetary motion. What is that guy's name? I can't think of it right now. He worked with Isaac Newton, though, and this is one of the things that prompted Newton to develop calculus. He came up with the fact that let me see if I get it right, the square of the period is proportional to the cube of the mean distance. What? Turned out that was very true. He didn't know why, though. He did an exercise a lot like this. I don't know if he used linear algebra. I assume he did. Kepler, there it is. His name's right down there. Johannes Kepler. And he discovered that relationship in 1619. He discovered the relationship then, but knew absolutely no reason why it was true. He went to Newton, and Newton did the analysis and had to develop a whole new branch of math called calculus to do the analysis, and sure enough came up with a physical explanation of why that was true. Good for them. So there's an astronomical application for linear algebra. Here's another one. Acoustical noise levels in cities. That's another. You get lots and lots of data. Acoustics are measured in decibels. Okay, decibel itself is a log transform itself, and number of cars compared to the decibel levels, density of population. You can do all sorts of analysis. Again, linear algebra comes in very handy. Now, the next thing is network analysis. These are much easier to do than polynomial fits. I don't mean to skip over polynomial fits, but they're just so tedious. But network analysis, I know that aren't both of you pre-engineers? Yeah, okay. If you are going into engineering, depending on what field, there's a good chance you're going to do some network analysis. In fact, now, James, did you say you're in Physics 1 or Physics 2? Say again? 2. Okay, got it. That's all right.
Physics 2.
Yeah, Physics 2. Okay. Now, in Physics 2, that's electricity and magnetism, right?
Yes, sir.
You're going to be doing Kirchhoff's laws, which is a way of network analysis. You haven't gotten there yet, though, right? Yeah,
No,
you'll
sir.
get there. Guess what? Linear algebra helps you. So let's start with just generic network analysis, and this could be your traffic flow problem, okay? I've got to keep this in front of me so the microphone will pick up well, okay? And you see on page 29, you see you have what I call a node, okay? They call it a junction. Both names are fine. You have something coming into the junction, 25, and you have two things leaving the junction, x1 and x2. Well, guess what? The junction can't pile up stuff, and neither can it be depleted of stuff. It has to be neutral. So guess what? The amount going out has to equal the amount coming in, and since you have x1 and x2 both leaving, x1 plus x2 is equal to 25. That's how we do junction analysis or network analysis. So let's do example 5. You've got it there in front of you, right? So let's do it. These are a bit easier to do than polynomial functions, and they're a bit more fun too, I think. Okay? Maybe that's because they're easier. All right, so let's look at junction 1 there. You see in the upper left corner. What is coming in? Well, let's do what's going out first. You see going out of that is x1 plus x2 is going out. What's coming in? Equal 20. Okay, now when I go to write that down, here's how I'm writing it. Okay, I'm writing it x1 plus x2 and left a bunch of space there equal 20. Why? Because we have 5 junctions. We're probably going to have 5 unknowns. So I need to have room for my other unknowns. So let's go to node or junction 2. Okay? Now, it doesn't really matter which way you have coming in or going out, which one you set on which side. But since you have the 20 leaving, I like to have that positive. So let's make what's coming in, oh no, let's do it the other way. x3 is the variable leaving, so let's have that be positive so that things leaving are going to be positive. Okay, let's say this. Okay, you can do it any way you want to. I'm going to tell you how I see that. Is x3 minus x4. x3 is leaving, x4 is coming in, so they have to have different signs. And that's equal to something leaving, and that's a positive 20 there, because things leaving are positive. So x3 minus x4 has to equal 20. Now let's make sure that makes sense. Another way to say that is what's coming in is x4 is equal to x3 plus 20. No, so I got it wrong. Okay, so x4, yeah, x4 coming in is equal to x3 plus 20 going out. Okay, I probably should have written it that way to begin with. Okay, so that means x3 minus x4 would be minus 20.
So if you're looking at it, the 20 is leaving junction 2.
Right.
Then x4 has to equal 20 as well.
Okay.
Because
Okay.
it has to be going in.
Okay. Here's how I really should have written this down. Let's look at what's going in and equals what's going out. And it doesn't matter which order. So what's coming in, x4 equal what's going out, x3 plus 20. Right?
Right.
That probably was the best way for me to express that one. x4 is equal to x3. Now, but I wanted to get it in the form of a matrix. So I wanted my x3 to be positive. So we'll keep that on that side. So I subtract x4, but then I have to subtract the 20. Now, there was nothing special there. I could have done minus x3 plus x4 is equal to positive 20. That would work just as well. But it's probably a good idea to write down at your junctions what's coming in equals what's coming out. And it doesn't matter which side you put either one of them on, but then rearrange it to fit into your matrix properly. Okay? So let's go to junction 3. So let's do it the way we finally decided. Let's put what's coming in equal to what's coming out. What's coming in? x2 plus x3, right? And that's equal to what's going out, 10 plus 10, that's 20. Okay, that's easy to write down. So that would be x2 plus x3 equal 20. Okay, so you see how I'm ultimately writing it. Okay,
Yes, sir.
Let's move to junction 4. What's coming in equals what's going out. What's coming in? x1
plus 10
plus 10 equals
x5.
x5. So if you rearrange that and make it x1 minus x5, right? Bringing that to the same side, that would equal negative 10. Now, there's no reason to pick them one way or another. Just make sure you're consistent. Make sure the equations work. So that's junction 4. Let's go to junction 5. You tell me what you would do.
All right, junction 5. You have 10. You have x5 plus 10 equals x4.
Perfect.
So then I can say x4 minus x5 equals 10.
Equals 10. That's a perfectly good way to do it. Okay? Now what we have here is a big old 5 by 6 matrix. But the good news is you have a lot of zeros in them. Okay? So let's do our matrix. You tell me what that matrix is. Now, you can, if you did different equations from me and you have minus signs and plus signs reversed, perfectly fine. I don't care. So what would be your matrix? Tell me.
I got 1 plus 1.
No, don't do a plus. Just 1, 1.
20.
Okay, but put 0,
Yeah,
0, 0, 20. You have to account for every variable.
Yeah.
Okay? I'll put a 2. That's 20. Okay, got it. Next.
You got 0, 0, 1, negative 1, 0, negative 20.
Perfect. Next.
0, 1, 1, 0, 0, 20.
Perfect.
0.
Oop, oop. 1, isn't it?
Oh yeah, okay, I skipped 1. There you go.
Okay, yeah. You could do any order you wanted to, yeah.
Right. 1, 0, 0, 0, negative 1, negative 10.
Okay. There was 3 zeros in the middle, right?
Yes, sir.
Okay, good. I couldn't hear how many you said. Okay. Next.
0, 0, 0, 1, negative 1, and 10.
Okay. 3 zeros, 1, negative 1, 10, right?
Yes, sir.
Okay. All right. There's a matrix, okay? Big old hairy matrix. What's the first thing you want to happen with that matrix?
I got a 1 down here.
Ah, that 1 in the upper left corner, we're happy campers, okay?
All right.
All right. Now, what you want below it?
0.
You got it. Next below that? 0, you got it. Oops, that next one, not. So how do you get that 1 to become a 0 in row 4?
Multiply the top equation by negative 1.
Yeah. Negative row 1 plus row 4 is the new row 4.
All right.
Okay. So, I'm going to set up my matrix here. Big old hairy matrix. Going right down the first. And this is what gets so tedious about linear algebra. Okay. That's why if you got a computer that'll do it, it's even tedious to enter the stuff, but once you do, it does all the heavy lifting. 1, 1, 0, 0, 0, 20. Next row was fine. 0, 0, 1, negative 1, 0, negative 20. Next one. 0, 1, 1, 0, 0, 20. Now, row 4 we're changing. What does it become?
0, negative 1,
Perfect.
0,
Get it?
0,
Yep.
negative 1,
Right?
and negative 30.
Negative 10. Oh, wait, no, you're right. Negative 30, you're right. I'm sorry, I got carried away. Okay. Negative 30. Okay? And the last row is perfectly fine. 0,
Right.
0, 0, 1 minus 1, 10. Okay. All right. Now, what's the next thing you want to happen? Let's review. You got a 1 in the upper left, and you got zeros below it. Okay, now, remember, this class goes to 1:15, right?
Yes, sir.
Okay, good. Don't let me run over. I have a meeting at 1:30.
Okay.
And if I miss my meeting, I'll be very, very upset. You know, I love those meetings. Okay. If you want to go till 5, I'm happy. Okay, no, I'm hungry. Okay, never mind. All right. What you want next? You got 1 with zeros below it. What you want in row 2?